All right, let's talk about a hidden superpower that's, believe it or not, probably humming away inside your computer this very second. We're going to dive into compute shaders, and I promise, by the end of this, you'll get exactly how they pull off their magic. Okay, let's get into it. Have you ever been deep in a game or watching some incredible special effects and just stopped to think, how in the world is that even possible? How can a machine keep track of every single raindrop in a storm or all the sparks from an explosion all at once without just completely freezing up? I mean, it seems like it should be impossible, right? But there's a really, really clever answer. And yeah, that answer is what I like to call the GPU's secret weapon, the compute shader. You see, for the longest time, the GPU, your graphics processing unit, it had one main job: draw stuff on your screen. And it had to follow a very strict step-by-step rulebook to do it. But compute shaders, they just throw that rulebook out the window, breaking free from that whole rigid process. So what is a compute shader, really? Well, think of it as a special kind of program that you run straight on the GPU. But here's the twist. Instead of being obsessed with drawing pixels, it's built for heavy-duty general-purpose number crunching. It lets us tap into the raw mathematical horsepower of the GPU for all sorts of things that have absolutely nothing to do with traditional graphics. And this really shows you the whole shift in thinking. The old way, the graphics pipeline, that was like a one-way assembly line, super rigid, built for one thing and one thing only, making pictures. But the new way, with compute shaders, that assembly line gets turned into a wide-open workshop. It's this incredibly flexible tool that lets developers use the GPU's muscle for pretty much any calculation they can dream up. It's a total game changer. So how does this all actually work under the hood? Well, the secret ingredient is something called parallel processing. And honestly, the best way to wrap your head around it is with a pretty simple analogy. Okay, so picture this. Think of your computer's main brain, the CPU, as one absolutely brilliant manager. This manager is a genius at handling really complex, one-at-a-time tasks that need careful, logical steps. But the GPU? The GPU is a massive factory floor, just packed with thousands and thousands of workers. Now, each individual worker isn't a genius, but they are incredibly good at doing the same simple, repetitive task over and over and over again, and they all do it at the exact same time. So, the process basically goes like this. A developer writes the instructions for that one simple task. Then, the computer takes a massive problem, like, say, calculating the physics for 1,000,000 raindrops, and breaks it down into thousands of tiny little jobs. We call these threads. Then it just sends that mountain of work over to the GPU's factory, and all those workers, all those threads, get executed at the exact same time. It's pure, beautiful, coordinated chaos. And this chart, well, this shows you the mind-blowing result of all that teamwork. If you give one of those massive, repetitive jobs to our brilliant manager, the CPU, it'll get it done, eventually. But give that exact same job to the GPU's army of workers using a compute shader, the time it takes to finish just plummets. I mean, look at that. The difference isn't just a little better, it is a revolutionary leap in speed. So when developers use these, the goals are super clear. First, process a ton of calculations all at once. Second, use that to slash the time it takes to get things done. This also takes a huge load off the main CPU, freeing it up to, run the rest of your computer. And critically, you keep all the data right there on the GPU, because moving massive amounts of information back and forth between it and the main memory is super slow. It's all about being smart and efficient. Okay, so we've covered the how. Now for the really fun part, the wow. Let's look at some of the absolutely incredible things that are being built with this tech, taking us from a few lines of code to entire virtual universes. First up, physics that just feel real. You know, when you see a cape flowing perfectly in the wind, or how hair bounces and moves so naturally, that's not a pre-made animation. That's thousands of individual calculations happening every single frame. And compute shaders are what make those incredibly complex simulations possible. And then you have stuff like this, living worlds. Instead of an artist spending months or even years modeling every single rock, tree, and mountain, compute shaders can generate vast, breathtaking landscapes just from a set of mathematical rules. It's called procedural generation, and it's what allows developers to create game worlds that are, for all intents and purposes, infinite. And this one brings us right back to where we started, massive particle systems. This is the magic behind hyper-realistic smoke, water spray, explosions, you name it. This is the perfect job for a compute shader. Each little particle's movement is a simple calculation, and the GPU's factory of workers can handle millions of them simultaneously without even breaking a sweat. But get this, it's not just about making things look pretty. Compute shaders are making AI smarter too. Figuring out the best path for, say, 100 different characters in a crowded city, that's a massive computational headache. But for the GPU's parallel processing power, it's the perfect problem to solve. And actually, this is the same core principle that powers so much of modern machine learning today. Of course, it can't all be sunshine and rainbows, right? This kind of incredible power comes with its own set of challenges. This isn't some magic wand you can wave at every problem. There are some really important limitations and trade-offs you have to think about. Let's just walk through this. So you get that massive parallel skeed, right? But the catch is it's useless for tasks that have to happen in order. Where step 2 absolutely needs the result from step 1. You get a huge performance boost, but if you have to keep moving data to and from the GPU, that can create a new bottleneck that slows everything down. And yeah, while this unlocks insane visual complexity, trying to find and fix a bug in shader code can be, let's just say, notoriously difficult. So if you're going to remember one thing from all of this, let it be this. Compute shaders unlock the absolutely massive calculating power of the GPU, letting us use it for tasks that go way, way beyond just drawing pictures. It's a fundamental shift, turning our graphics cards into these little general-purpose supercomputers. And that kind of leaves us with a pretty wild thought to chew on. With this kind of power, we're getting closer and closer to being able to compute and simulate reality itself right inside our machines. It really makes you wonder, doesn't it? What are we going to create next?